Okay, so it's being recorded. So one note, this is being recorded as always. So if you want to, I mean, in this in today's meeting, you can actually unmute yourself and ask questions if you want to. But just I assume that you are giving consent for the video to be posted online. So if you don't want your voice to be recorded, you can just ask questions in the chat. Okay, so let's get started. So we're talking about scheduling in multiprocessors. We primarily talked about two different approaches that could be used. One was having a single ready queue for all the CPUs, and one was having separate queues for each CPU. And we discussed that this is going to cause a main problem, and that main problem is basically load balancing between these queues. We talked about multiple options, what can be done in order to load balance the queues. One option was to make sure that all queues have the same number of threads. We talked about why this is not a good idea, because each thread might have different weights, and we kind of we're ignoring that, where we if we just care about the number. So then we said, okay, what if we multiply the number by the weight, and then make sure that the queues are load balanced with that new metric, which is basically the sum of the weights for each thread on each queue. And the problem with that was also, as we discussed, the fact that we're ignoring how much each thread is going to be using the CPU. So if you have one thread with really high weight that uses the CPU so not frequently at all, so it only uses the CPU for a small amount of time and then goes for I/O. If you end up equalizing the weight, then you will have the situation where one of your CPUs become idle or unutilized. So the third option is to just mix all these different metrics and come up with one which would consider the weights and also consider the utilization. And that's basically what is used in today's Linux. So the notion of weight is basically the multiplication of, the notion of weight is the sum of weights times utilization. So if let's say, just an example, let's say I have a situation where I have on CPU 1, I have task 1 and task 2, and then on CPU 2, I have task 1, task 2, all the way to, task 2, task 3, all the way to task 12. So basically, or 11, let's say 10 tasks. So I have 10 tasks on CPU 2 and 2 tasks on CPU 1. Let's say that the weights for all the CPU 2 tasks are 1. So the weight is 1, the weight is 1. Excuse me. And the weight of this one is 1. And let's say the weight of each one of these is 5. So if I just go with the sum of weights, now this system is load balanced because the sum of weights on this is 10, the sum of weights on this is 10. So if I go with the weights, this is load balanced. Now let's assume that T1 utilizes the CPU only 50%. And T2 utilizes the CPU by 50%. So each one of them, for the, let's assume that actually, to make this even easier, to do the calculation. Let's say the two of them together utilize the CPU for 50%. So let's say this CPU is idle 50% of the time. But let's assume that all of these guys utilize the CPU 100%. So the CPU utilization, this is utilization. So if the utilization of CPU 1 is 50% and utilization of CPU 2 is 100%, so 1, then now these two CPUs are not load balanced, because if I multiply this utilization by these weights and this utilization by this weight, I have more load on CPU 2 than I have on CPU 1. Now, this is just a toy example. I'm not assuming or I'm not expecting you to know how exactly the load is calculated, because it's actually not straightforward. But the purpose of this slide is to just show that we have different metrics to consider when we want to load balance our system. And there are different things to be considered when you want to do this calculation. Usually the weights are managed in Linux using C groups. Again, something that I'm just throwing out. If you know about C groups, so you should have heard about it. But if you don't, then that's fine. But when you have C groups, if a thread creates, or if a process creates a new process, or if a process creates new threads, all of the threads that are created by the same process go to the same C group. Now, this C group is basically a term that people use for like an umbrella for all the threads and all the tasks that are in the C group. And then you want to weight C groups. So if one C group has twice as weight as another C group, then that C group is expected to get twice as much CPU time as the other one. And it doesn't matter if tasks in one C group or if processes in one C group creates more processes, because all of them are going to be in one C group, and we're going to assure fairness across C groups. So creating more threads, more processes is not going to help the thread or the process to get more CPU time. But again, that's basically just advanced topic. We're not going to cover that. Okay, so so this slide is just a little bit of history again. That as you remember, the CPU scheduling was considered as a problem that is solved around 2000, but after we started having multiprocessors, people started paying attention to this. And again, initially people thought that load balancing is easy, but it was proven that it's a hard task. So eventually, the paper that was published in 2016 showed that that load balancing is absolutely hard, and the Linux scheduler at the time was failing to provide what was necessary. Now, because load balancing is hard, so if you think about load balancing, what if your CPUs are not load balanced, whatever your load metric is, how do you make them load balanced? Well, to make your system load balanced, you have to migrate tasks. So you have to grab one of the tasks in a CPU that has a high load and then migrate it to another task. Now, what does this exactly mean? As far as the CPU, as far as the operating system is concerned, it just means that you're going to assign the TCB of this task to this new process, this new processor, and start running the code for this task on a new processor. But as far as the performance of this task goes, this could mean a lot of overhead. As we discussed previously, a task that is migrated to another CPU has to warm up the caches, the private caches, the shared caches, and potentially the memory. And this has high overhead. Now, because load balancing has overhead, and also calculating the load, like, you have to do some calculation to realize that your system is not load balanced. Whatever your metric is, you have to calculate that metric for different CPUs, and then you have to make some computation to see if the load is balanced or not. And if the load is not balanced, then you have to make a decision to make some migrations to make it balanced. So all of this is overhead. Now, what happened as time passed by, people gave up on load balancing because it was so expensive. Now, the alternative to load balancing is to wait for a CPU to become idle. And at that time, when your CPU becomes idle, then go and steal work from others. So, when you do load balancing, if your system is completely load balanced, then either all CPUs are working or all CPUs are idle. So that's perfect situation if your system is load balanced. But if your system is not load balanced, then a time comes where one CPU or two CPUs or three CPUs become idle when other CPUs have work to do. So basically, the end result was that let this happen, because if we want to make it load balance, it's going to be expensive. So let's not do that. Let disaster happen, meaning that let get to the point where one or two or one or few CPUs become idle. And at that point, go and steal jobs or steal tasks from the CPUs that are not idle. So basically, that's this last bullet. So we're going to avoid running this load balancing procedure until something goes wrong. And what is going to go wrong is one CPU is going to get idle when other CPUs have work to do. And at that point, we do what is called work stealing. So basically what you do, you find the most loaded CPU, and then you steal a task from that one. Now, for work stealing, it's, again, there are so many different things that you can do, but the idea is basically what I just described. Okay, so I'm going to end load balancing here, so I'm not going to go deeper than that. Now I'm going to talk a little bit about other aspects of scheduling in multiprocessors. So I think all I want you guys to know is, scheduling in multiprocessor is hard, and there are heuristics, but there is no perfect solution to solve all of them. So things like work stealing these are heuristics that people have come up to solve the problem. So we're far away from assuming that the scheduling problem has been solved, because it hasn't. So whatever solution we have is kind of like heuristic to solve the multiprocessor scheduling problem. And turns out that it's actually a very hard problem, even mathematically. So I'm going to just avoid talking about it. Okay. Now let's talk about other things, other topics that might come up with multiprocessors. One of the things that come up with multiprocessors is processor affinity. So what does this mean? So process affinity means a mapping between tasks or threads or processes to processors. Now, we talked about migration. Migration basically means changing this affinity. So if the affinity of task 1 or thread 1 is CPU 1, migration means that I'm going to change this affinity and put this thread on another CPU. Now, there are different kinds or types of affinity. One is soft affinity. So the user could define an affinity that is soft. The soft affinity means that the operating system tries its best to schedule a certain task on a certain CPU, but there is no guarantee. So if that's not possible, operating system can and will migrate your task somewhere else. There is also hard affinity. So hard affinity means that the user wants a specific task to only be scheduled on a specific CPU. So this is basically hard affinity. Operating system should and will honor this affinity. Now, the other thing that I'm going to just circle back to the beginning of the lecture on multiprocessor is the effect of NUMA on scheduling. So again, I'm not going to go deep into this. I'm going to just scratch the surface and give you some idea why paying attention to NUMA matters. So in this figure in front of you, let me see if I can make it bigger. Yeah, I can. So I'm showing you a relatively new AMD processor. Now, on the on the left-hand side, I have a CPU or a multi-core processor with NUMA, and the number of NUMA nodes that you can see in this picture are 3. So we talked about NUMA, right? We talked about non-uniform memory accesses, and that meant that each CPU has a local memory that is fast to address or access, and there are other memory banks available on the processor, but the time it takes for you to go and access the memory banks on those is higher. Now, fix a core. Let's say we fix our core here. We want to consider cores that are here. So the local memory for these guys is this one. So this constitutes NUMA 1 with respect to the cores in this cluster. So these guys, any core in NUMA 1, they can access this memory here very fast. Now, any memory here, here, and here, so this 1, 2, and 3, these memory banks, they take the same amount of time to be accessed by any core in NUMA 1. So if you want to access this, it means that you have to go one hub away. The same with this memory. You have to go one hub away. And for this one, you have to go one hub away. So we can cluster all of them and say this becomes my NUMA 2. Now, I'm repeating myself. It's with respect to cores in this NUMA. So for any core in this NUMA, they have a cluster NUMA 0 or NUMA 1. And then all these cores in this cluster are considered NUMA 2. Now, if you want to now go and access memory here, 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 and here, so let's call it 4, 5, 6, and 7. Now, this takes 2 hubs. You have to first go to NUMA 1, and then you have to go to NUMA 2 to access memory. So these cores are 2 hubs away. Now, based on the distance that these cores have, we're going to have different NUMA levels. Now, why is this important? Why are we talking about this? The reason that we're talking about this is that if you have to migrate, so if times come that either you want to steal a work or you want to migrate a task, then it's important to migrate the task or steal a task from a NUMA node that is close to you. So if you steal a task, let's say you're here and you become idle and you want to steal a task, it's better for you to steal a task that was running on NUMA 2 rather than stealing a task that was running on NUMA 3. And the reason is obvious, right? Because if you steal a task from NUMA 2 and start running it on NUMA 1, then this task is going to access its data, which resides in NUMA 2 memory. And that takes time for that data to be brought to NUMA 1. And if you steal a task from NUMA 3, then you're going to spend a lot more to bring the data for this task back to NUMA 1. So it's important to know how many NUMA nodes you have in the system with respect to any processor when you want to make a decision on migrating or stealing a work. So best option is to have only one NUMA. So best option is to not have NUMA and have uniform memory access. So basically one NUMA node altogether. So everybody is in one NUMA node. In that case, you don't have NUMA. You have uniform memory access. But the less NUMA you have, the better. So there is a competition right now in computer architecture to make sure that the memory is accessed uniformly. And making these so this is a newer design, the picture on the left, on the right. So it has the same number of processor cores, but it has less NUMA. You know, designing these technologies, this is a hard thing to do, but seems like we're moving to that direction because this one, the picture on the left, adds a lot of difficulty when it comes to load balancing, because you have to consider all these NUMA nodes and then consider the affinity of tasks in the NUMA nodes that they're running at, and it adds a lot of overhead to a scheduling. So having less NUMA nodes improves the efficiency of your scheduling policy, because you don't need to consider the difficulty of accessing your data. Okay, so we talked about that. Now, let's talk about one more thing, and that's basically scheduling new tasks. So when you create a new tasks, where should you assign that task to, right? So when we're talking about load balancing, we're talking about already existing tasks and trying to balance the load on the system by moving them around. When a new task is created, then we have an option to set the affinity, right? We can do whatever we want because the task has not yet started. So we have a clean slate. Now we want to make a decision to assign the task to a core in the most efficient way possible. Now Linux, usually what it does, so this is typically what is done in Linux. When a parent thread or parent process creates new tasks, new threads, the new threads are assigned to the same processor as the parent thread. And this sort of makes sense why you would want to do such a thing. The reason for doing this is basically if this is a thread running in the same process, then it's with high probability going to access the data that other threads in this process have access to. So if I assign it to the same processor, I'm kind of guaranteeing that the data will be local to this newly created thread. However, this is kind of like a suboptimal decision to make. Actually, before talking about suboptimality, let's also talk about newly awakened threads. So I talked about newly created threads. Let's also talk about threads that went for I/O and came back, right? So I was running this thread, it did I/O, and I suspended it. So I haven't been running this thread for a while. So probably I don't care about its memory anymore because I haven't been running it. Now the I/O is done and I want to run the thread again. So these threads are very similar to each other, the situation for both of them, right? Both of them, we have kind of like a clean slate, and it's important to make a decision where we want to assign them. Again, the what happens in Linux is usually you put a thread where they went to sleep. So if a thread was running on CPU 1 and then it did I/O, and now it's coming back, you might have a tendency to put it back on the same CPU that it went to sleep. Now, this is fine. This, you could do it, but if your system is not fully loaded, if your system is not highly utilized, you might be missing on the opportunity to load balance your system. Think about it. So your system, let's say your system is load balanced completely, and you start creating new threads on one of your CPUs. If you put all the new threads on the same CPU that they were created, then you're basically making your load unbalanced because all the new threads are going to go to the same place. The same with newly awakened threads. If a bunch of threads went for I/O and then you load balance your system and now they want to come back, if you put them back where they were initially, you might lose your balance again. So one strategy that you could use, instead of blindly put them where they are created or blindly put them where they went to sleep initially, is to run your load balancing algorithm every time you create a new thread or every time a newly awakened thread comes back. So you could basically look at the load on your system and then assign them to the least loaded CPU. Now, this is a little bit tricky when you're calculating the least loaded CPU. You have to be careful that you're not just looking at the current moment, because you might have the situation where, let's say CPU 1 is assigned, let's say, I don't know, 10 tasks or 10 threads. And these threads, let's say they run and then they go for I/O. They run and then they go for I/O. They run and then they go for I/O. So the utilization of this CPU is like 50%, let's assume. So 50% of the time the CPU is working and 50% of the time the CPU is not working. Now, if at the moment at the moment that I have created a new thread, if I look at this CPU and I see the CPU being idle, so let's say I'm lucky, I look at the CPU when it's idle. So as I said, this CPU is going to be idle 50% of the time and will be running 50% of the time. So if I look at the CPU when it's idle and say, oh, this CPU is idle, so I'm going to put my newly created task there, then I might be missing the point that, well, it is now idle, but in a bit, 10 tasks are going to come and use the CPU. So probably you want to not only look at idle CPUs, you want to look at the CPUs that are idle for the longest period of time. So you want to look back in time and make sure that the CPU that you're assigning has been idle for a long period of time. Now, again, this is just a heuristic, right? There is no mathematical proof that if you do this, then you will end up having the best scheduling policy possible. But, heuristics like this come up a lot because the problem that we're facing is a hard problem. Okay, now let's switch gears and talk about another topic that we talked about at the beginning and see how that one affects scheduling. So one of the features of multiprocessors that I mentioned 2-3 lectures ago was heterogeneity. I talked to you about the new designs that we have, for example, our cell phones, our iPads. Now, some of the laptop processors are going to this direction as well. So the processor might have a bunch of high performance CPUs and bunch of low power CPUs. And in a mobile phone or in a tablet, this makes a lot of sense because, you know, if you're playing a game with your cell phone, or if you're running an application that needs CPU, you can use the high performance CPUs. The problem with them is that they're going to get hot really soon because they're going to consume more power. So the performance comes with a power cost. So at some point you don't want to use them because if you keep using the high performance ones, you're going to burn the cell phone. So then you switch to the low power ones to still run the jobs that you have, but save power. And, you know, if battery is important to you, you might want to run as much as you can on the low power ones. If the temperature of your cell phone is important to you, you want to do that as well. Now, this adds another challenge to the already challenging problem of scheduling multiprocessors, because, you know, so far I talked about load, I talked about performance, but now we have another metric that we have to care about, and that's energy and power. So this, you know, this slide, again, scratching the surface, talks about energy aware scheduling. This is another scheduling available in Linux. So the goal of this scheduling policy is to minimize the amount of energy that your tasks consume. Now, different tasks consume different amounts, or different threads consume different amounts of power. Not all of your applications that you're running on your system are the same when it comes to their power consumption. One of the most power hungry resources on your processor is your cache. So if you have a application that uses a lot of memory and cache, that application might get your CPU, your system really hot. The other resource that does this is registers. So if let's say you have a I don't know, matrix multiplication application, an application that uses a lot of register, a lot of computation, that could also make your processor hot. But if you have an application that does a lot of I/O, for example, it's not going to make your processor hot. So depending on the application and what resources on this on the board that the application uses, you're going to consume different amounts of energy. Now, the energy aware scheduler tries to consider all of these factors and minimize the amount of energy that you're consuming by allocating CPUs to tasks in a smart way. So one of the ways that this could be done is you can calculate this metric that is called performance per watt. So you can measure whatever metric of performance you have. Usually in systems is instruction per second. So this is something that you can count on your processor. You can see how many instructions you have executed. You can also read how much power you have consumed for that many instructions. And then you can calculate the performance per watt metric for different applications. And this metric changes as you change the allocation. So if you allocate your task on CPU 1, which is, like, let's say, high performance CPU, it could consume X amount of power. If you allocate your task to CPU 2, which is a power efficient processor or CPU, it might consume a lot less, maybe X divided by 4. So you make in EAS, or in energy aware scheduling, you start experimenting with this. So very similar to what we talked about when we talked about the predictions, if you remember. So you sample your system. So you run your task on different CPUs and you measure performance, you measure power, and you create a history of you gather data on these metrics, and once you're confident about your model, once you're confident that this particular application consumes this amount of energy on this CPU and this other application consumes this amount of power on this other CPU, then you can make a decision on assigning them so that your assignment minimizes the total amount of CPU that you're consuming. So with this one, you create an energy model, which could be kind of like a table that shows you how much power each application consumes and how much performance it gains on different CPUs. And then you might have a capacity, basically how much work can be done on different CPUs. The other metric that I kind of didn't talk about is frequency. So, you know, having fast or big CPUs and, you know, performance efficient CPUs and power efficient CPUs is one design. The other design that you can have is to just change the frequency of your CPUs. So you probably have heard about turbo boosting. So with turbo boosting, you basically increase the frequency of your CPU. And by increasing the frequency of your CPU, you make your CPU faster, but you also exponentially increase the power consumption of your CPU. So this is another metric that the scheduler can actually tune. So you might not only want to allocate tasks to CPUs, you might also want to set the efficient or the best optimal frequency for each CPU for each task. So that's basically what EAS does. I'm not, again, as I mentioned, I'm not going to go deep into what this does, but scratching the surface, that's what you get. So you construct these models, and then you use what you learn about applications to then do the scheduling and do the allocation of CPUs, setting affinities for different tasks. Okay, now to just finish up the entire section on scheduling in our discussions, uniprocessor scheduling and multiprocessor scheduling. Let me just go through the history or a recent history of Linux CPU schedulers. So one of the first CPU schedulers in Linux was the ON scheduler. So that was the name. So it was the default scheduler in Linux kernel version 2.4 to version 2.6. Now, the reason that it was, so this one was kind of like a simple implementation of the multi-level fair queuing, the one that we saw. The downside of the scheduler was its complexity. So that's where this ON comes. It was kind of like a linked list. So in order for you to search between the tasks in your system, you have to pay order of n, n being the number of tasks in your system. So this was good for early systems, but when we started having really heavily multi-threaded workloads where you have thousands and hundreds of thousands of, not hundreds of thousands, but thousands of threads, then paying ON becomes expensive. So every time you want to schedule, you have to, you know, go through all 1,000 tasks that you have in your system, and that's expensive. So to solve this, around 2003, the next scheduler was introduced. It was called O1 scheduler, and as you might imagine, it's not hard to see. We changed ON to O1, so it used a better data structure to sort tasks, so that when we want to search and find the highest priority task, we don't need to pay order of n. This is probably something that you guys want to look at when you're designing your schedulers for P2. But anyhow, this was kind of good in terms of, you know, reducing the cost of searching and going through tasks, and it worked well with multi-threaded. The difficulty with this was what we discussed, I think I don't exactly remember, like while ago when I was talking about predicting and classifying applications. So one downside of O1 scheduler was that it was trying very hard to classify applications into different groups. It was trying to classify applications to interactive applications and non-interactive application. And when an application got to be classified as an interactive, it would increase its priority because it wanted to achieve low response time. So if the O1 scheduler recognizes that an application is interactive, it would boost its priority. And boosting priority means that the application is going to get more CPU time. Now, at the surface, this is cool, this is good, this is what we want, but the difficulty is you will, no matter what you do, you're going to have false positives. You're going to have false negatives as well. So you're going to misclassify. And when you misclassify, that could have consequences. You might misclassify a non-interactive application as an interactive application and give it more CPU time. And by doing this, you might take away the CPU from actual interactive applications. So this really backfired. So although the data structure was good, but this notion of classifying applications backfired. So very soon it changed. So this was from version 2.6 to version 2.6.22. So in kernel version 2.6.23, the scheduler changed from O1 to completely fair scheduler. So completely fair scheduler kept this efficiency, but had to sacrifice O1 for O log n. So it was still better than ON. So it was changed from, we first went from ON to O1, but then from O1 to O log n. But it had a better fairness allocation. So a better fair allocation. And the fair allocation was based on what we saw in uniprocessor scheduling. It's very similar to max-min fairness, weighted max-min fairness. Now, this has been the default Linux scheduler even now. So from 2007 to now 2022, completely fair scheduler has been the default scheduler. It's a very complicated scheduler. So I myself have attempted multiple times to read the code, understand it. It's just too complicated, at least for me, to understand, because it has so many patches and so many different things have been added to it. So, you know, you could imagine load balancing, stealing jobs, different notions of virtual time. So it's a very complicated scheduling. The underlying idea is max-min fairness, but it has a lot of different patches. Now, around 2009, another scheduling policy was introduced. It's called brainfuck scheduler, or BFS. So this was to get rid of the complexity of CFS, because CFS has become, or had become, and still is, a very complicated scheduling policy. So the idea behind this BFS was, let's have a really simple scheduling policy that everybody can look at the code and understand what's going on. Now, one of the decisions that they made was, actually only one person was involved in designing BFS, but the decision that was made was to have a single queue in a multiprocessor. Now, that decision works kind of well if your system doesn't have many CPUs, but if you have many CPUs, then it will fail. So, you know, if you have servers with 128 cores or 256 cores, then BFS is gonna just completely blow up your system. It's gonna be really bad. So an extension to BFS is is a multiple queue skip list scheduler. So BFS has been kind of archived. Nobody uses it, or maybe if somebody uses it, it's going to be like academic or just learning, but it's not deployed. Now, this other one kept the underlying idea that you want the scheduler to be simple, but also efficient for multiprocessors. Now, this is not a complete list. As I said, the default is basically complete fair scheduler, BFS, and multiple queue skip list scheduler are scheduling policies that were kind of like sideline schedulers. They never became mainstream scheduler. In fact, they were not meant to be mainstream. But this area remains to be explored, really. So I don't consider the problem of scheduling to be nearly done in modern modern systems. Okay, so again, I'm going to switch gears one more time and talk about scheduling multi-threaded programs in multiprocessors. So one scheduling that you can have is oblivious scheduling. So basically, in oblivious scheduling, when you're load balancing, you don't really care about the threads, what threads you have in your system. So it's you look at different threads as being independent. So if, let's say, all these purple boxes here, they are different threads of process 2. The green boxes are different threads of process 1. And the orange boxes are different threads of process 3. Now, the one option is to assume that all these threads are independent. So you can look at them as units of scheduling and then try to load balance your system. And that could lead to a setting like this, what you're seeing right now on the screen, where, you know, I have tasks from, or I have threads from 2 different processes on CPU 3. I have tasks, threads from different processes on CPU 2, and I have the same here on CPU 1. And when, you know, we talked about each CPU having its own scheduler. So when CPU 1 is scheduling its tasks, it doesn't have any idea that 2 different threads from this process are assigned to another CPU. It doesn't care. It doesn't pay any attention to the fact that different threads for this same process might be running on different CPUs. Now, this assumption makes it easy to load balance. It will make it easy to schedule. But the downside of this is, what if these threads are dependent? So what if they're not independent? For example, let's say that this guy here, P2.1, locks a mutex, right? So let's say at some point here, so this is time going down, this is time. So let's say at time t, this thread locks a mutex. Now at this time, t plus epsilon, we're going to context switch. So this CPU2 makes a decision to context switch for whatever reason. So now P3.2 is running. And, you know, this is fine. You can do that. But very soon, CPU 1 is going to start running P2.3. Now, because this thread 1 locked the mutex, if CPU 1 starts running the third thread, and this thread wants the mutex, then it's going to be blocked. So because of the dependency, because this task depended on the first one, and because this dependency was ignored, this thread might actually get blocked. If CPU 2 knew or cared that there is another task there is another thread from this process that is going to run, it might have let P2 run and finish before interrupting it. So just to recap, in Oblivious scheduling, all the threads are going to be assumed to be independent. And this makes it simple. The downside is, in reality, they are dependent. And if you do not orchestrate the scheduling on different CPUs, you might end up wasting CPU cycles and having to block your threads as they execute. Now, if you want to have some notion of orchestration between your threads, you have to know their dependencies. How are threads dependent? So this actually talks about the problem with Oblivious scheduling. Actually, before talking about the problem, let's talk about this notion of bulk synchronous parallelism. So this is very common in systems. So this is basically what is done in MapReduce, if you have heard of it. This is usually the case with TensorFlow applications, with PyTorch applications. This is true with many of the big data machine learning applications that you have. They are mostly data parallel. So for example, with machine learning applications, you have huge databases that you want to classify. The classification code is the same. So you have one piece of code that classifies, but you have a huge amount of data. So one way to parallelize is to break your data into smaller fractions and then run your code on different pieces of data. This is called data parallelism. Now, every here and there, you might need to kind of synchronize between your tasks. For example, I don't know if you know about MapReduce, but let's say you want to count the number of words in a big document. So let's say you have, I don't know, few gigabytes of documents, and you want to do a word count. You want to know how many times any specific word has been repeated in your document. So one thing you can do is you can just divide your documents into smaller fractions, and then on each fraction count the number of words that are repeated in that fraction. But once you're done with this step, you need to sum them up. So it might be that word Apple or word Microsoft has been repeated 10 times in one document and 20 times in another document and 100 times in another document, but you want to know how many times it has been repeated in your entire data set. So once you do run your algorithm on each part, you need to reduce this. You need to now kind of accumulate the result of all these executions. So this is basically the synchronization that you need. So you run your tasks on different CPUs. Then at some point, you're going to stop. They're going to send messages to each other. Let's say each each process tells anybody else how many different words they have counted, and then they sum it up, and now they have an idea about how many times each word has been repeated. And you could then go ahead and do some other computation again in parallel. So this is called bulk synchronization, which again comes from data parallelism. Now, if you have such application and decide to do oblivious scheduling, meaning that you decide not to care about dependency between your tasks, obviously, as you can see here, this thread 1 is dependent on thread 2 and thread 3 because of this synchronization step, right? It has to wait for these two to send it its data. Now, if CPU 3, for some reason, decides to do a context switching, and instead of running the thread, context switch to another thread and run some other thread, because it doesn't know that other threads are waiting, then your entire application gets a slowdown that you can just see here. So CPU 1 and CPU 2 are done, and they're just waiting for CPU 3 to finish this third thread. So this is the problem. This is the downside of oblivious scheduling. You could end up degrading the performance of your entire application by making a mistake in scheduling one of the tasks. So maybe this was not necessary. Maybe this context switch could have waited. But because you didn't have the idea that other tasks are running on other CPUs and they depend on you, they need you, then you made a wrong decision, and you basically, the wrong decision cascaded, and you ended up wasting a lot of performance, leaving a lot of performance on the table. There are other types of parallelism. It's not always data parallelism. The other type of parallelism that you might have is producer-consumer parallelism. This is a one that we've seen in the past. So in this one, you have different threads sending each other messages in a pipeline. So let's say, I don't know, like let's say you have an application, data comes in, you first classify your data, you recognize different objects in your image. Then you might have another thread that looks at, analyzing different, let's say it recognizes the speed of different objects in your system. And then you might then pass that data to another thread, which then does planning. So it's, let's say you're writing this application for your self-driving car. The images are coming from your sensors. The first task is object detection. The second task is, let's say, a speed recognition, a speed identification. And the third one is planning to maneuver around this object that you have detected, given the speed of it and the speed of your own car and stuff like that, right? So you have this staged manner of computation. Now, if you have such system, and if you have oblivious scheduling, then you could actually screw up the performance of your system pretty badly. Let's say CPU 1, which everybody depends on, makes a decision to context switch between thread 1 and another thread. Let's say thread 4, that is totally unrelated. Then the entire data flow will stop, and your performance will sink. So this is another example where oblivious scheduling will show, great negative impact on the performance of your application. So that's another example. Now, one way to deal with multi-threaded applications so let me actually say something here. Although oblivious scheduling is, as you saw, is bad, but let's face it, it's basically what is implemented everywhere. So this actually is very similar to deadlock. If you remember from 252, you saw how bad deadlock could be, but hopefully it was communicated to you that most operating systems don't care about deadlock at all. So they just let it happen and then deal with it. So the same thing about Oblivious scheduling. We know that it's bad, but really dealing with it is harder than dealing with the consequences of Oblivious scheduling. So I'm pausing here and saying that, look, Oblivious scheduling is bad, but scheduling multiprocessors is hard. Scheduling multi-threaded applications is hard. So usually this is what you get in most systems. Now, let's say you want to fix this. So whatever I'm going to talk now is kind of like theoretical and academic, not really something that has been used in systems. But one approach that you could take is called gang scheduling. So in gang scheduling, you make sure that all the threads from all the applications are scheduled at the same time on all of your CPUs. This will make sure that if they depend on each other, then they get to run at the same time. It's kind of like you're giving the entire system to each process every time you schedule one task from that process. So as you can see, during this time period, all my CPUs are running process one's threads. During this period, all my processors are running P2 threads, and so on and so forth. Now, this is good in terms of dependency because we're basically honoring the dependency. But as you can see, and as is obvious from this picture, it's really bad in terms of CPU utilization because you're wasting these times here, right? So this is a time where, you know, one or two tasks or one or two threads are done, but you're just extending this period because another thread is still running. You could have used this time here to run a new thread, but because you want to give the entire system to P2, then you have to make this decision. Now, one way to deal with this is instead of giving your entire system, all your CPUs to each process, instead of doing that, you could divide your processors between your processes. So you could potentially, this is one example, you could allocate 3 of your CPUs to one process and the rest of it to another process. So this way, you kind of, you know, get rid of the waste that we had in the gang scheduling. So this is called space sharing. Now, making a decision on how many CPUs to give each process is a hard decision. So it's not intuitive how you should make this decision. How many CPUs should you give process 1? How many CPUs should you give process 2? In general, if you look at the performance of your multi-threaded application, so in this graph that you can see, on the y-axis I have performance, on the x-axis I have the number of processors or number of CPUs that I'm allocating to each one of the applications. So if you have a perfectly parallel application, let's say you have data parallelism and there is no communication between tasks, so and you have a lot of data. So if I have 10 CPUs, I will be running 10 tasks per second. If you give me 20 CPUs, I will be running 20 tasks per second. So in a perfect world, my performance would go up linearly with the number of CPUs that you're giving me. Now, this is too good to be true. This usually never happens. Usually never. But it's very rare for you to have a perfectly parallel application. what you usually see is you have diminishing marginal returns. So your performance is going to go up almost linearly for a while before it starts to for the returns to diminish. So what is the return? So the return basically is how much performance am I gaining from an extra CPU. So this is basically how much performance I gain. This here is how much performance I gained by adding an extra CPU. Now, if I add another CPU, and then I measure this again, so this time the performance improvement, so I'm now comparing these arrows. So the performance improvement diminishes. So I have diminishing marginal returns. So if I looked at, like, for example, here, for example, and one extra CPU gives me this much performance gain. And as you can see, this is just shrinking. As you give me more CPUs, I can use them less and less. And in most cases, there is actually a limit on how far your performance could get. So at some point, adding extra CPUs is not going to help you at all. So it kind of like plateaus. Your curve plateaus. You don't even have this diminishing marginal returns. You get zero return from an extra CPU. This is something that you have to consider when you're doing a space sharing. When you're making a decision how many CPUs to give each processor, you have to have some notion of how to allocate your CPUs. One model that we have is called Amdahl's law. Amdahl's law is a very old and very, very, very effective formula that comes very handy when you're dealing with with parallel applications. So Amdahl's law puts an upper bound. This is important. It's an upper bound on the amount of a speed up you can get. So it gives you the theoretical upper bound on your speed up for an extra CPU. Now it's usually less than that because it's giving you an upper bound. So in reality, you usually get less than what Amdahl's law tells you. Now let's look at Amdahl's law. What is it? So let's say I have a task or I have a thread. This is T1. Now T1 has serial portions and parallelizable portions. So the serial portions are kind of like the what we discussed, for example, with the word count example. This might be the portion where you're summing up your results. And then this portion of parallelizable is the portion that if I give you extra CPUs, you can run your application in parallel. So the serial portions, you can only run it on one CPU. The parallelizable portions, you can speed it up as many CPUs as you can you have. So now if I have a task and I give my task only one CPU, then it doesn't matter if I have a serial portion or I have a parallelizable portion. All of them are going to run on a single CPU. Now, if you give me 4 CPUs instead, now what happens? Well, the serial portion of my application is just going to use the same one CPU. It's not going to use the extra 3 CPUs that you have given me. However, the parallelizable portion of my application, I can shorten it by making it parallel, right? For example, if I was, going through 4 GB of data on one CPU, now I can go through 1 GB of data on each CPU. So each one of them gets smaller, 1/4 of how much it took on one CPU. I'm going to spend 1/4 of that if you give me 4 CPUs. So, and the same for all the serial portions, the execution time is not going to change. So the execution time remains the same. For the parallelizable portions, the execution time is divided by the number of CPUs that you're giving me. Now, if I want to measure speed up, what is a speed up? A speed up, if you give me X processors, is how long it takes for me to run on one CPU divided by how long does it take me to run on X CPUs. Now, we're going to keep T1 in the numerator, but in the denominator, let's say that F is basically the parallelizable portion of your application, then 1 minus F is the serial portion of your application. Now, for the serial portion of your application, execution time doesn't change. So 1 minus F times T1 is the serial portion of your application. Doesn't matter how many cores you give it. But for the parallelizable portion, which is F times T1, this is the parallelizable portion. The more CPU you give me, the less it's going to take time for me to execute. So it's going to be FT1 divided by X. Now I can cancel out T1 from this equation, and I get this nice formula here, which is basically Amdahl's law. So this is Amdahl's law. So Amdahl's law says if the parallelizable portion of your application is F, then the maximum speed up you can expect given X processors is X divided by X times 1 minus F plus F. Now, if you draw this, if you this is just an equation. We can draw this for different Fs. So in this graph on the y-axis, I have a speed up. So basically, how much a speed up I can expect. On the x-axis, I have number of cores. So this is X. How many cores I have. Now, different colors show different Fs. So this is the parallelizable portion. Now, you can see that if only half of your application is parallelizable, it would be this blue curve here. So this blue curve is kind of like the plateaued example as we saw. So even if you give me 65,000 CPUs, my speed up compared to a single CPU is just 2. I speed up my application by a factor of 2 with 65,000 CPUs because I can't use it because half of my application is serializable. I cannot use any of these cores for that. Now, this green curve all the way here is when you have 95% parallelizable. So if your application is 95% of your application is parallelizable, this should be really good, right? This is super good if you have an application that 95% of the jobs are parallelizable. Then, as you can see, with 65,000 CPUs, you can expect 20 times extra CPU. This is super depressing, actually. So it's far, far away from being linear, right? I have 65,000 CPUs, and compared to having one CPU, my performance has increased by a factor of 20. So this gives you an idea of how bad it is to have any serial portion in your application. And in most cases, it's unavoidable. So you always have these serial portions no matter what. And Amdahl's law gives you an upper bound on this. Now, I'm going to skip over this other one, which is called the carp flat metric. So just to set up the problem here, let's say you go to a company and you write a parallel application, multi-threaded application, and then your boss comes one day and asks you what portion of your application is parallelizable. Even if you're a wonderful programmer, chances are you have zero idea what portion of your application is parallelizable. So knowing this F So in the previous plot, I assume that I know f. I assume that f is 50%, 90%, 95%, whatever. But if you write an application and somebody asks you what portion of your application is parallelizable, you probably won't have any idea. So one thing you could do is to go and reverse Amdahl's law. So what you could do is you could measure your speed up with X processors. So you could run your application on one CPU and measure the execution time. Then run your application on, let's say, 200 CPUs and measure your execution time. And then put everything that you have in this equation, and then you have a single variable here, a single unknown, which is f, and then you can calculate this f. So let's say for x equal 20, I ran my application on 20 cores, and I got, let's say I got I don't know, 10x. I'm so sorry. Let's say I got 10x improvement. Now I have everything here. I can just calculate f. So this is the formula. So if you have your speed up, you can get it by measurement, and you have x, then you can calculate f. Now, one thing about this is the question you might ask is, for what x should I measure my speed up? Because I can measure my speed up with 20 cores, I can measure my speed up with 200 cores, I can measure my speed up with 10 cores. What should I set x? Now, if everything was ideal, it wouldn't matter. If you set x to 10 or 20 or 100, it wouldn't matter. If Amdahl's law was perfect, then it wouldn't matter what you set x to. In reality, however, x, this notion that I defined here is idealistic. So this says, if you give me 4 CPUs, I'm going to just divide this time by 4. In reality, this is not going to be the case. Like, it's not going to be if I give you 200 CPUs, you're going to divide this to 200 pieces. Because you have overhead. So in reality, even the parallelizable portion has to have some overhead. So it's not going to be completely, infinitely parallelizable. So as a result, Amdahl's law is not perfect. It's just an upper bound. So we actually wrote a paper on this. We studied different parallelizable applications. We changed this x. We measured the parallelizable portion, and lo and behold, it actually, for some applications, it works. So it doesn't matter how you change x. But for most of the applications, if you change x, the fraction that you get is different. Okay, so I'm going to end it here. So hopefully from next on Thursday, we'll start talking about real-time operating system and real-time systems. Okay, thank you for sticking around. Sorry for the technical difficulty, and we'll talk to you on Thursday. Take care. Be safe. Bye-bye.